In the vast darkness of the universe, nothing is still, nothing is permanent, and nothing survives untouched by gravity. Galaxies, those majestic islands of stars, may look serene from afar, but they are not quiet structures. They twist, collide, merge, tear each other apart, and grow by consuming anything smaller that drifts too close. In the cosmic hierarchy, the rule is simple: the big devour the small. Across billions of years, this silent violence has shaped the architecture of the universe. Large galaxies drift through space accompanied by swarms of smaller companions, and sooner or later, gravity pulls those companions inward. Their stars stretch into long tidal streams, their dark matter halos unravel, and their ancient cores dissolve into the larger host. Galactic cannibalism is not a curiosity, it is the primary engine of galactic evolution. Even our own Milky Way is not innocent. It has swallowed entire dwarf galaxies in the past, and at this very moment, more of them are falling toward us, already being shredded by the galaxy's tidal forces. We live inside a cosmic predator, a galaxy built from the remains of countless smaller ones. This is the story of how galaxies grow, transform, and sculpt the universe, not through peaceful expansion, but through gravitational hunger. In a cosmos ruled by mass and motion, cannibalism is not chaos, it is creation. Galaxies consume one another for a simple but profound reason. Gravity builds the universe from the bottom up. In the earliest moments after the Big Bang, matter was distributed unevenly. Some regions were slightly denser than others. These small variations collapsed first, forming the tiniest structures. Over billions of years, these small systems merged into larger ones, and those larger ones merged again into something even more massive. This process, known as gravitational hierarchy, is the foundation of cosmic evolution. Everything grows by assembling what came before it. But galaxies do not merge in isolation. Each one sits inside an enormous, invisible sphere of dark matter, a halo far larger than the galaxy itself. These halos act as gravitational traps, pulling in nearby dwarf galaxies like stones falling into a deep well. Once a smaller galaxy crosses into the halo of a larger one, its fate is sealed. It begins to spiral inward, stretched by tidal forces, losing gas, stars, and dark matter. Long before the final collision, the cannibalism has already begun. The vastness of space might suggest that such encounters are rare, but on cosmic scales, they are inevitable. Galaxies travel in groups and clusters, held together by gravity. They move through the same gravitational landscape, orbiting centers of mass, crossing paths again and again over billions of years. When hundreds or thousands of galaxies share the same cluster, collisions become not just likely, they become unavoidable. This is why galactic cannibalism is not an anomaly or an act of cosmic violence. It is a natural, continuous process, the primary mechanism through which large galaxies grow and evolve. Without these mergers, massive galaxies like the Milky Way or Andromeda would never have formed. The universe constructs its grandest structures through collision, assimilation, and transformation. In this sense, cannibalism is not destruction, it is creation on the largest imaginable scale. Surrounding the Milky Way is a silent swarm of companions, dozens of dwarf galaxies, each containing only a tiny fraction of the stars found in our own. They drift through the halo like cosmic minnows swimming beside a great whale. Some of them, such as the Sagittarius dwarf and the Canis Major dwarf, are so stretched and distorted that they barely resemble galaxies at all. They are already being pulled apart, their stars unraveling into long celestial streams that wrap around the Milky Way like threads of ancient silk. Dwarf galaxies are fragile. Their masses are small, their gravitational pull weak, and their stars held together only loosely. When they venture too close to a larger galaxy, tidal forces begin to tear them open. Imagine stretching a handful of sand between two hands. Grains fall away, the structure collapses. In space, gravity performs a similar act, stripping stars from the dwarf galaxy bit by bit. Over millions of years, the dwarf dissolves entirely, its stars absorbed into the larger galaxy's disk or halo. But this destruction is not meaningless. It is the primary mechanism through which galaxies grow. Dwarf galaxies act as the building blocks of the cosmic world. Every massive galaxy, including the Milky Way, is a mosaic of past collisions, stitched together from countless small ancestors. Their stars become part of the galactic halo, their dark matter thickens the galaxy's gravitational core, and their gas seeds new generations of star formation. Even today, the Milky Way continues this slow, inevitable feast, pulling in nearby dwarfs as they cross the boundary of its dark matter halo. In the grand story of galactic evolution, dwarf galaxies are the raw material, the cosmic bricks from which larger structures are built. And every time one is consumed, the galaxy that devours it becomes a little brighter, a little bigger, a little more complete. When a dwarf galaxy is pulled apart by the gravity of a larger one, it does not vanish instantly. Instead, its stars unravel slowly, stretching into long, ghostly ribbons that wrap around the host like the remnants of a shredded tapestry. These are stellar streams, the lingering scars of ancient encounters, frozen into the sky as reminders of past collisions. As the Milky Way continues its slow feast, many such streams encircle us. One of the most striking is the Helmi Stream, discovered in 1999. Its stars move together like a forgotten river of light, the remains of a small galaxy consumed billions of years ago. Another is the Leviathan Stream, an enormous, recently discovered structure, a sprawling ribbon of stars likely formed from a massive early merger that reshaped the Milky Way's inner halo. The Javelin, Arrow, Stream cuts through the galaxy like a thin, sharpened line, evidence of a smaller system shredded with precision by tidal forces. But the most famous of all is the Sagittarius Stream, produced by the ongoing destruction of the Sagittarius dwarf galaxy. This stream loops around the Milky Way in great arcs, wrapping our galaxy several times. It is so extensive that it forms a nearly complete ring, a visible signature of a dwarf being torn apart even today. The Sagittarius dwarf itself is just a dim remnant, a gravitational corpse, still sinking into the Milky Way's halo. These streams are not merely poetic artifacts, they are scientific gold. For much of history, they remained hidden, faint, diffuse, nearly invisible against the dense background of millions of stars. But today, thanks to the extraordinary precision of the Gaia mission, astronomers can measure the motion of individual stars across the entire sky. Gaia reveals which stars move together, which share a common origin, and which form coherent lines across space. With its data, these once invisible structures suddenly appear in breathtaking clarity. Through stellar streams, we can reconstruct the Milky Way's ancient meals. Each stream is a chapter in our galaxy's long history of cannibalism, a record of the smaller worlds it absorbed on its path to becoming what it is today. They are cosmic fossils, delicate, luminous scars that whisper the story of how galaxies grow. When two large galaxies collide, the encounter is not a clean, orderly merger. Their gravitational fields pull violently on one another, stretching and distorting their disks until immense arcs of gas and stars are flung outward into space. These spectacular structures are called tidal tails, long, curved bridges of stellar light that can extend for tens or even hundreds of thousands of light years. They are the cosmic equivalent of debris scattered across a battlefield, material torn away by the raw force of gravity. Tidal tails form because stars and gas clouds on the outer edges of a galaxy are only loosely bound. When the galaxy passes near another massive system, tidal forces tug at different regions with different strengths, pulling the outer layers outward while the core resists. Over millions of years, this creates sweeping, elegant curves that arc far into the dark. These tails are not static. They evolve, twist, fragment, and sometimes even collapse under their own gravity, giving birth to new dwarf galaxies formed from the torn material. In a sense, galactic cannibalism does more than destroy, it can also create. Some of the most iconic examples in the universe come from interacting galaxy systems. The Antennae galaxies display two immense tidal tails, each stretching out like wings of scattered stars, a visual testament to the violence of their merger. The Mice galaxies show long, slender tidal streams trailing behind them as they sweep past one another in a gravitational dance. The Tadpole galaxy features one of the longest and most dramatic tails ever observed, a bright arc of blue stars almost 300,000 light-years long. Each of these systems illustrates the extraordinary beauty that arises when galaxies collide, tear each other open, and reshape themselves in the process. Tidal tails are not merely decorative. They record the history of galactic encounters, preserving the trajectory and mass of each participant. By studying these luminous arcs, astronomers can reconstruct past mergers, understand how galaxies evolve, and observe how material redistributes itself across enormous scales. They are both a signature of destruction and a blueprint for creation, the visible aftermath of cosmic violence sculpted into breathtaking form. The Milky Way may look peaceful from our vantage point inside one of its spiral arms, but beneath its graceful structure lies a long and violent history. Our galaxy has not grown quietly. It is a predator, one that has consumed multiple smaller galaxies over billions of years, each leaving behind unmistakable traces. Today, Astronomers can identify the remains of these ancient victims scattered throughout the sky, woven into the very fabric of the Milky Way. One of the most striking examples is the Sagittarius dwarf galaxy, a small, elongated system currently being torn apart in real time. As it orbits the Milky Way, tidal forces stretch it into multiple arcs, forming the immense Sagittarius stream, which wraps around the galaxy like a glowing ribbon. The core of the dwarf still exists, but it is collapsing, sinking deeper into the Milky Way's halo. This is cannibalism unfolding right now, an ongoing meal we can watch from within. But the most dramatic victim is far older, the Gaia Enceladus galaxy, also known as the Gaia sausage. Around 10 billion years ago, this galaxy collided with the young Milky Way in a catastrophic merger. The event was so powerful that it reshaped the entire structure of our galaxy, puffing up the stellar halo, heating the disk, and altering the orbits of millions of stars. The stars from Gaia Enceladus still move together today, following elongated, chaotic trajectories that betray their ancient origin. Their chemical fingerprints, especially their low metallicity and unique abundance ratios, confirm they were born in an entirely different system before being absorbed. Another dramatic remnant is the Sequoia dwarf galaxy, a system devoured long after Gaia Enceladus. Its remains form a distinct population of stars with retrograde orbits, meaning they move around the Milky Way in the opposite direction from most of our galaxy. This unusual motion is a direct imprint of the dwarf's original trajectory before it was destroyed. Once again, the chemistry of these stars reveals their foreign origin. They carry ratios of magnesium, iron, and heavy elements inconsistent with stars formed inside the Milky Way. Taken together, these mergers did more than add stars to our galaxy. They reshaped the Milky Way's structure, thickening its disk, building its halo, feeding its central black hole, and enriching its dark matter halo with the mass of the destroyed dwarfs. Every major component of our galaxy bears the scars of these ancient collisions. The stars we see overhead at night are not a single family. They are a mosaic of dozens of smaller civilizations of stars, long dead but still shining. What we call the Milky Way is, in truth, the graveyard of many galaxies, a vast stellar city built from the bones of everything it has consumed. The disk of the Milky Way looks calm from afar, a smooth, flat whirlpool of stars turning around the galactic center. But when astronomers examine it closely, they find that the disk is not smooth at all. It ripples, it bends, it oscillates, it carries scars, subtle but enormous disturbances that run across thousands of light years. These are the echoes of ancient collisions, the silent footprint of galaxies that once slammed into us, leaving behind waves that still roll through the stellar sea. One of the clearest signs is the presence of vertical waves in the disk. Instead of lying in a single flat plane, millions of stars gently bob above and below the mid-plane like water rising and falling after a large ship has passed. These oscillations are not random. They form coherent patterns, bending modes, breathing modes, and rippling shapes, all pointing to one conclusion. Something massive struck the Milky Way and set its stars in motion. For years, astronomers suspected the culprit, and with precise Gaia data, the evidence has become overwhelming. These wrinkles in the disk betray the influence of repeated mergers, most famously the impact of Gaia Enceladus, whose violent arrival billions of years ago sent shockwaves across the young Milky Way. But even more recent intruders have left their marks. The Sagittarius dwarf galaxy, still being torn apart today, has passed through our disk multiple times. Each pass was like a galactic seismic event, shaking the entire system, pulling on stars, lifting some upward, pushing others downward, and giving the disk a warped, asymmetric shape. These disturbances did more than create waves. They subtly tilted the entire disk, producing the slight warp we observe today in the Milky Way's outer regions, an enormous curve stretching thousands of light years above and below the plane. This warp is not static, it twists and rotates like a slowly turning spiral, another sign of gravitational torques left by past mergers. In essence, the Milky Way's disk behaves like a vast, flexible membrane responding to ancient impacts. Every star that rises or falls, every wave that passes across the spiral arms, and every asymmetry in the thickness of the disk is a memory, a record of collisions written into motion rather than stone. These are our galaxy's dynamic scars, its seismic history encoded in the movement of hundreds of billions of stars. By studying these oscillations, astronomers can reconstruct the Milky Way's past as if reading geological layers, except here, the layers are waves of starlight rippling through cosmic time. When galaxies consume smaller companions, The most dramatic transformations do not occur in the visible stars, but in the invisible realm surrounding them. Every dwarf galaxy travels through space wrapped in its own halo of dark matter, an enormous, diffuse cloud that outweighs its stars by factors of hundreds or thousands. These halos are not rigid shells. They are gravitational envelopes, extending far beyond the visible galaxy and shaping the way it moves, rotates, and evolves. When a dwarf galaxy approaches a larger one, the first contact occurs not between stars, but between halos, two invisible oceans of mass beginning to overlap and merge long before the galaxies collide. As tidal forces tear the dwarf galaxy apart, its dark matter halo is the first component to be stripped. Gradually, it becomes part of the larger galaxy's halo, adding mass to the host and subtly reshaping its gravitational architecture. The shape of the big galaxy's halo changes as well. Sometimes it becomes more elongated, sometimes more spherical, depending on the angle and velocity of the infalling dwarf. These mergers act as a slow but persistent sculpting process, continuously updating the galaxy's gravitational blueprint. This is not a cosmetic change, it has profound consequences for cosmology. The growth of dark matter halos through cannibalism is one of the major predictions of the CDM model, the standard theory of the universe. The model proposes that structure grows hierarchically. Small halos merge into larger ones, which merge into even bigger systems, eventually forming galaxy clusters. By observing how galaxies absorb dwarfs, and how their halos adjust, astronomers are effectively watching this cosmic hierarchy unfold in real time. Moreover, the distribution of dark matter in the Milky Way today carries the memory of every galaxy we have consumed. Streams of stripped dark matter extend across the halo like invisible rivers, while dense clumps known as subhalos continue orbiting long after their parent dwarf galaxies have vanished. These features influence the rotation curve of the galaxy, the motion of stars in the halo, and even the way gravitational lensing bends light from distant quasars. Understanding how dark matter halos grow through galactic cannibalism is essential for testing our theories of the universe. If the way halos merge did not match simulations, if their shapes or masses were inconsistent, the entire cosmological model might need revision. But instead, observations confirm the theory. Cannibalism is not only a stellar drama, but a dark matter symphony, shaping galaxies from the inside out. When two galaxies collide, the impact is not an immediate crash of stars but a profound disturbance of their gas. The interstellar medium, normally a delicate balance of cold clouds, warm diffuse gas, and hot cosmic plasma, is violently stirred. As the galaxies interpenetrate, their gas clouds collide at high speeds, creating shock fronts that ripple through the system like cosmic earthquakes. These shocks compress vast regions of gas, setting off bursts of gravitational collapse. Suddenly, entire swarms of new stars ignite, forming in clusters so dense and bright that they briefly outshine the rest of the galaxy. This burst activity, known as a starburst event, can be so powerful that it transforms the galaxy's appearance. Thousands of massive young stars pour out ultraviolet light and stellar winds, inflating bubbles and superbubbles in the surrounding gas. As these energetic winds combine with the turbulence from the merger, they launch enormous galactic fountains, streams of gas hurled thousands of light-years above the galactic disk, only to cool, condense, and fall back like slow cosmic rain. But mergers do not always trigger creation, they can also suppress it. The same shocks that trigger starbursts can heat large reservoirs of gas to millions of degrees, preventing it from collapsing into new stars. In some collisions, especially when supermassive black holes are activated, the outflows become strong enough to blow gas permanently out of the galaxy, shutting down star formation for hundreds of millions of years. Thus, mergers act as both creators and destroyers. They are the engines that mix, heat, cool, and recycle galactic gas. They sculpt the life cycles of galaxies. Whether they spark brilliant new generations of stars or extinguish future ones, their imprint is unmistakable, towering fountains rising from the chaos of collision, carrying the chemical seeds of future worlds. Galaxy mergers are not gentle encounters, they are transformative events that can rewrite the very structure of a galaxy. In ordinary circumstances, spiral galaxies maintain their elegant, rotating disks through a delicate balance of angular momentum and gravity. Their thin arms, rich in gas and young stars, trace graceful patterns around a stable center. But when two large galaxies collide, this balance collapses. The orbits of billions of stars are violently scrambled, gas clouds lose their ordered motion, and the disk, once a flat, rotating plane, thickens, twists, and eventually disintegrates. This chaotic restructuring is what turns spiral galaxies into ellipticals. Elliptical galaxies are not born, they are made. They are the fossilized remnants of once dynamic spirals that have been churned into spheroidal, featureless shapes. In the turmoil of a major merger, stars are flung into random trajectories, losing their coherent rotation. Over time, the galaxy settles into a new equilibrium, rounder, smoother, and devoid of the cold gas needed to form new stars. What remains is a glowing, aging population of red, ancient stars, suspended in a diffuse halo. This process is not theoretical. We are watching it happen in slow motion within our own cosmic neighborhood. The Milky Way and the Andromeda Galaxy are on a collision course, closing in at roughly 110 kilometers per second. In about 4 billion years, their halos will touch. In 5 to 6 billion years, their disks will interpenetrate in spectacular waves of tidal deformation. Spiral arms will stretch like ribbons, star clusters will be flung outward in tidal tails, and vast clouds of gas will collide, igniting short, intense bursts of star formation. By the end of this celestial dance, neither galaxy will resemble its former self. The Milky Way, once a structured spiral with defined arms, will lose its disk entirely. Andromeda's structure will collapse as well. After several close passes and a final merger, the combined remnant will stabilize into a massive elliptical galaxy, often called Milkomeda. Its stars will orbit in every direction, its gas supply largely exhausted by starbursts and black hole activity. It will shine more brightly, yet appear smoother and redder, a monument to the violent creativity of gravitational evolution. This morphological transformation is central to the grand story of cosmic architecture. Through galactic cannibalism and collision, the universe continually reshapes itself. Spirals grow into giants, giants fuse into massive ellipticals, and each merger contributes to the slow construction of ever larger cosmic structures. In the end, morphology is not a fixed identity. It is the evolving imprint of a galaxy's past encounters, written in stars, gas, and the scars of ancient collisions. Galactic cannibalism is not a brief chapter in the history of the universe. It is the rhythm of cosmic evolution itself. From the first billion years after the Big Bang to the present moment, galaxies have grown by consuming one another. In the early universe, this process was especially fierce. Space was smaller, galaxies were closer together, and gas-rich dwarfs swarmed around young proto-galaxies like moths around a flame. Every encounter, every collision, every gravitational tug left an imprint. Streams of stars, warped disks, disrupted halos, and the steady rise of massive galactic cores. But even though the universe has expanded dramatically, the process has not ended. The cosmos has simply changed tempo. Today, the mergers happen more slowly, but they are no less impactful. Around the Milky Way alone, dozens of small dwarf galaxies still orbit like satellites destined for assimilation. Some are actively being torn apart at this very moment, their stars stretched into delicate rivers across the sky. Others lie in elongated orbits, quietly approaching their fate. Cosmic cannibalism is not a destructive accident. It is the mechanism by which galaxies grow, evolve, and transform. It governs the flow of dark matter, redistributes gas, and shapes the architecture of galaxy clusters. Over billions of years, small galaxies feed the large galaxies collide to become giants, and giants eventually merge into colossal ellipticals at the hearts of clusters. It is a cycle that does not pause, because gravity never tires. Even the future of our own galaxy is sealed within this long, patient violence. The Milky Way continues to absorb dwarfs while simultaneously being drawn toward Andromeda. The slow drift across intergalactic space is simply another step in the endless dance of gravity, a dance that began with the first structures in the young universe and will continue for as long as galaxies exist. In cosmic time, cannibalism is not an exception. It is the rule, the heartbeat of galactic evolution, echoing across billions of years and shaping the universe we see today. We often imagine the Milky Way as a peaceful, spiraling island of stars drifting quietly through cosmic darkness. But its true nature is far more dramatic. Our home galaxy is a predator, shaped by billions of years of consuming others. Every layer of its structure, its halo, its thick disk, even parts of the thin disk, carries the memory of ancient collisions and devoured neighbors. The Milky Way as we know it today is not a singular entity born whole, but a composite being forged through countless mergers across cosmic time. Many of the stars we see in the night sky are not native to this galactic city. Some were born in foreign worlds, Dwarf galaxies that approached too close were torn apart and dissolved into long, graceful streams. Their stars now orbit among ours, indistinguishable except to the precise eyes of Gaia. In a very real sense, we live among immigrants from distant stellar nations, stitched into the fabric of our galaxy by the relentless pull of gravity. Our stellar siblings may have originated in forgotten galaxies that died long before Earth even existed. As we look outward, we are also looking backward, into the remnants of ancient galactic feasts. The halo that surrounds us is a graveyard of shredded worlds. The disk we inhabit carries scars from past impacts. Even the future is already written. The Milky Way will merge with Andromeda, and together they will become an entirely new, larger being. The cycle does not end with us. We are simply witnessing one moment of an eternal process. The poetic truth is this: we are descendants of countless galactic worlds, fused into a single river of stars. Our existence is the echo of cosmic violence, yet also of cosmic creation. Out of destruction came structure, out of chaos came beauty, out of the merging of galaxies came the home we now inhabit. The night sky above us is not only a map of stars, it is a story of origins, migrations, extinctions, and rebirths. And in that grand tale, we are a tiny but luminous part.